Thank you, Emily. Well, and thank you all for coming, young and old. Tonight has been 5 years in the making, actually. And actually, if we want to go back even farther, we had a show that opened in 2009 called Journey to the Stars. Can I see a show of hands of some of you who may have seen Journey to the Stars? Good. Actually, I see a fair number, and that's wonderful. How many of you have never been here before? About the same number. That's good. What I mean about this being a show in preparation for about 5 years is that some of you have come to our live programs and have seen this interactivity where we present live, and that allows us to explore our digital universe database. And about 5 years ago, we had an idea to begin to explore this interactivity, but really to look at dynamical simulations and be able to do what we've done previously with our space shows. Our space shows pivot on data visualization, and we like to show the process. That's what astrophysics is all about, is applying the laws of physics to understand the dynamics and how the universe operates. And so the notion for new software came up. We have been using a product which was developed here as a collaboration with Linköping University, which is Sweden's leading technological university, together with Gothenburg. Gothenburg was also, I guess, really prior to Linköping. Linköping was developed around the location of Saab Aerospace, and I believe founded around 1967. And so we've been collaborating thanks to Professor Anders Innerman, who came to us because he saw that we were doing shows of immersive data visualization. And what he teaches is advanced computer graphics, data visualization. They do research in how to actually push the frontiers of data visualization. So with this idea of creating new software, we call this OpenSpace. If you're interested in finding out more, you can go to a website, OpenSpace Project as one word. So OpenSpaceProject.com. And when we began to talk about this, Journey to the Stars came out in 2009. And that looked at the process of stars. And what better star to look at than our own sun and understand that? So we put together a number of simulations to visualize that and understand the process of the sun. And we did that because we had some connections down at NASA headquarters in heliophysics. Leila Gutakrata, who was deputy, I believe, at the heliophysics division, science mission director at heliophysics, and she introduced me to a team at NASA Goddard. And the director of that team is with us tonight, and this is Masha Kuznetsova. Masha, can you please stand up? Masha is going to present to us. Masha is the director of the Community Coordinated Modeling Center for Space Physics, Space Weather Research. And it's at NASA Goddard Space Flight Center, but it is also partially funded by the National Science Foundation for educational activities, research in the ionosphere, and perhaps last but not least, of most importance tonight, also helping to fund the students from Linköping University who come over and do their master's thesis project for parts of building OpenSpace. Those two students are going to be helping us drive tonight, and they are in the pilot seat. And this is really their first time operating the dome, but they are operating the software that they wrote that visualizes the results of this space weather modeling. I'd like to introduce both of them. I want both of you to stand up. This is first up is Oscar Kalbaum and Michael Novem. And they have worked tirelessly, and the team arrived on Saturday. We began. Some of the team came on Sunday. We've had some late nights in putting the show for you together. I also want our code master of OpenSpace, who has just begun his postdoc at NYU. He got his PhD in data visualization at Linköping University, and that's Alexander Bach. So without further ado, I want to turn this over to the deputy director of the CCMC, and that is Leila Mays. And the last thing I'd like to say about the CCMC group, they operate out of NASA. I was talking to Masha that it is one of the most international groups of scientists that I think I've ever met. And I think today's world that's really needs emphasis. And so, Masha, you're originally from Moscow. And Leila, you are Iranian. You were born here, but spent some time there. And team members from Finland, you said the Philippines, Puerto Rico, even one, I guess, new team member from Nepal, South Korea, and Europeans. So it's just an incredible team, and I think it just really emphasizes what we like to show here in showing the universe, is that we show we're all riding on this one little planet. Leila, take it away. Thank you.
Okay. Thank you, Carter, for that great introduction. So I guess let's bring the lights down and start the show. So today we're going to talk about space weather. Space weather is what I study and forecast at NASA. At the Community Coordinated Modeling Center, we do space weather research, and we also do some forecasting, some research-based forecasting to predict space weather effects for NASA missions. So today I'm going to be showing you data from spacecraft observations and also simulations that we use to interpret these observations. So first we're going to fly to the sun. So Michael is our first pilot for the evening. He's flying us to the sun. And that's because the sun and its magnetic field is the ultimate source for space weather throughout our solar system. The sun's magnetic field influences a bubble-like region called the heliosphere, and that goes actually far beyond the orbit of Pluto, about 3 times as far. And when I talk about magnetic fields, you can think of a bar magnet. Maybe when you were growing up, you tried putting iron filings around the bar magnet, and that actually traces the magnetic field lines of force. So you can imagine that when I talk about magnetic fields. So what we're looking at in the center there is an SDO image, a Solar Dynamics Observatory image of the sun in July 2012. SDO was is in Earth orbit observing the sun. So let's fly to the Earth and take a look at the orbit of SDO. And the reason why we're showing you July 2012 is because this is a very interesting time for space weather. Right now, the sun is actually kind of boring, so we're not showing it to you right now because we're in solar minimum. In 2012, we were in solar maximum, and there was a lot more activity. The sun actually has an 11-year cycle. So we're zooming in there. So Michael removed the labels. The first orbit that you're going to see there is actually, I don't think we're showing the moon orbit. So this is the orbit of SDO. Oh no, there we go. That's the moon orbit. I got them mixed up, the lighter colored orbit. And let me show that to you with the laser pointer. So this is the moon orbit. And now we're zooming in closer to the Earth. The white orbit is the orbit of SDO. And it's orbiting the Earth like this because it's constantly looking at the sun and it's taking images so often and at such high resolution that it needs to be in this tight orbit around the Earth so it can always be beaming down that data to the same satellite dish because it's just a vast amount of data. So now we're going to look at SDO's viewpoint towards the sun along this drawn there, and we're going to take a look at an image taken by the spacecraft. So let's just travel along SDO's field of view and slowly fly back to the sun. And we start to see the yellow sun that everyone is probably most familiar with. This is the sun's photosphere. This is the sun's directly visible surface. Its temperature is 5,800 Kelvin. That's about twice the temperature of the filament in an incandescent light bulb. So it's actually not that hot. It's a temperature we can achieve on Earth, but the core is much harder. So Alex, could you put up the image of the sun's interior layers for everybody? And so while he does that, I'll tell you about the core. It's actually 14 million Kelvin. So it's so hot in the core that we have hydrogen converting into helium in a process called fusion, and light is released in that process. It's also so hot that the sun is made up of plasma. That's not the plasma that you have in your blood, but it's the electrically charged hydrogen and helium particles that have become ionized. So they're all throughout the sun. Above the core, we have the radiative zone, and that's where the photons, the particles of light, can really just bounce around very freely. Finally, there's the convection zone, and in that layer, the temperature is about 2 million Kelvin, and there we have hot bubbles of plasma that rise to the surface and then fall back down as they cool off. That's very similar to if you're boiling a pot of water on the stove and you have those bubbles. That's the same process. So you have these convection flows. And then finally, we end up with the photosphere, the yellow sun. That's the layer that you see there. So we can remove that image of the sun's layers, and there's more to the sun than just the photosphere, actually. The sun has an outer atmosphere, and that is called the solar corona. And the Solar Dynamics Observatory observes the corona in 10 different channels or wavelengths, each highlighting a different temperature. So let's now travel through all of those different wavelengths and layers. So this is the first one. This is a little bit hotter. It's just above the photosphere. And here you can see this web-like pattern. You can also see it in the next wavelength. There we go. And here, this is an echo of those convection cell patterns that are below the photosphere. Next, we have the chromosphere, and here you can see these dense swirls of plasma. You can especially see them at the limbs very nicely. And then we have these bright regions. The temperature here is about 50,000 Kelvin. And this is actually cool compared to the next layers we're going to get to. So if we go to the transition region, this is where the temperature abruptly transitions from 50,000 Kelvin to a few million degrees Kelvin. And this is actually an open problem in our field. We don't understand why the sun, this layer of the sun heats up to a few million degrees in such a short distance in this layer. So let's go on to the corona. And now you can really start to see the atmosphere of the sun. We're at 1.25 million Kelvin. You can see the bright regions there. There's also some dark regions that we'll talk about soon. And this is another coronal channel where you can really see the sun's atmosphere. So there's more to the sun than just the yellow ball that we see. Now, the sun's magnetic field controls all of its dynamic activity. So let's go back to the chromosphere channel and look at a time sequence of some dynamic activity. So we see these loops of plasma and also some eruptions from here. Now these loops of plasma that you see, they're actually giving us an idea, a hint of the sun's magnetic field. And that's because the sun's magnetic field guides the motion of the plasma. So now if we go look at a coronal channel for the same time sequence, you can see also lots of loops of plasma all over the place here. Up here, we have some more. So because plasma is made up of charged particles, it means they must travel along magnetic field lines. And so these loops really give us an idea of those field lines. Now let's zoom out a little bit, fly out a little bit. Thanks, Michael. And we're going to be looking at data from two other spacecraft. It's a pair of twin spacecraft called Stereo. And we're zooming out because they're at Earth's orbital distance. It's called Stereo Ahead, Stereo A, and Stereo B for Stereo Behind. So Stereo A is up here, and then we have Stereo B, and Earth is down here. And then we have these lines showing you the viewpoint that they have of the sun. So Stereo A is going ahead of Earth's orbit, and it has all the same instrumentation as Stereo B. So it really gives us this dual viewpoint. And for the first time, it allows us to simultaneously view all around the sun. And this period that we're showing you right now was in July 2012. Now the plane of all these orbitic plane, because most of the planet's orbits lie in this plane. So let's fly in a little bit and take a look at the images taken by Stereo A first. So we can see a different angle of the sun. It doesn't look the same as what we see from SDO. There's a lot of dynamic activity. And then let's fly around and look at Stereo B. And on this viewpoint, you'll also see that the sun looks different from this side. So being able to view all the way around the sun really allows us to track the sun. So now let's slowly project these images onto the sun sphere to really get an idea of the 360 view that we get. Yeah, that's really cool. So now let's fly around a little bit to the viewpoint, and you can see all of the loops that we've been talking about that hint at the magnetic field of the sun. But scientists also use simulations in addition to the data that you see here, the spacecraft observations, to understand the sun's magnetic field. So let's overlay one of these simulations. What we're looking at is magnetic field lines, so the magnetic force field lines of the potential field source surface simulation. This is from Dr. Mark DeRosa. And this is tracing out what we think the sun's coronal magnetic field looks like. It represents the most steady and simple solution for the corona. And we can see that the loops that we had in the data are roughly matching those that we see in the simulation. So it really helps us better understand what's going on. So let's fly around a little bit, maybe to this dark region here. And you can see it's a bit darker than the surrounding areas. That's because this is a coronal hole. So here, there's less radiation emitted, and that's why it appears darker. But this is actually the main source of solar wind particles. And the reason for that is that the magnetic field lines of force from this region are nearly radial. And so that allows the particles to just easily stream out away from the sun. And if we look at a perspective here, as Michael has done, you can see that there's these radial field lines. Particles can just freely stream out. And this constant stream of particles is formed by the pressure difference between the sun's corona and interplanetary space. So now let's fly a little bit to SDO's viewpoint, rotate a little there, and then we're going to switch to another instrument from SDO that measures the sun's magnetic fields. So what you're seeing here, the black and white regions, they represent the magnetic field strength and direction. So the black and the white represent polarities, and then the gray means that the magnetic field strength actually isn't that high at all. So we have most of the field strength concentrated here in what we call active regions. Now let's turn on some particle flows that we're going to put on those field lines. And that really allows us to see, you can think of those as arrows. It allows us to see the magnetic polarity. So we see inward magnetic polarities going into the white region, and you see black is outward polarity. You see the flows coming out of the black regions. Now in the active regions is a few thousand Gauss. It's stronger than the surrounding. It's only 1/10 the strength of a refrigerator magnet. So most of the magnetic field is concentrated here. So now let's turn off those flows and we'll keep on the, let's keep that on. Yep, that looks great. And let's now switch to the photosphere image of the sun at the same time. For the same time step. There we go. So we see the sunspots here. They actually are just exactly above those regions of strong magnetic field, the black and white concentrated areas. And that's because where you have the strong magnetic field strength, that emerges through the photosphere, and that causes that area to cool slightly. So from that area, less radiation is emitted compared to the rest of the sun. And sunspots are about the size of the Earth, so you could fit the Earth into one of these spots. And they can last for days, but usually they can last for weeks as they rotate around the sun. So now let's go back to the magnetograph. And let's turn off the coronal simulation. And let's look at a time sequence so that you can look at the dynamics of these active regions. Right, so these active regions are constantly evolving. As we start to zoom in a little bit, you'll see that there are some dynamics there. You can see around each one of these areas, there's some flows. Now, the flows on the flows inside of the sun, the plasma flows, are what produces the sun's magnetic field. And different parts of the sun actually rotate at different rates. This is called differential rotation. And near the equator, the sun rotates pretty quickly. It's about 25 days. And then when we go to the poles, it steadily decreases to about 34 days to go once around. Now, this differential rotation causes the magnetic field of the sun to really wind up, and that will shear these active regions apart, and that will have them slowly also migrate towards the equator. So the sun's magnetic field is very important for understanding space weather. It's really the basis of all of the dynamics that we have. So next, let's look at a very interesting space weather event on July 12th, 2012. So let's switch to the coronal channel. And let's unproject this image from the sun sphere, just so that you can see the outer corona a little bit better. And let's rotate a little bit and get that into view. And I also want to point out that you have these two regions here. They're forming above and below the equator. And that's because of that differential rotation, because the equator is rotating faster. We usually get these belts of activity. Okay, so now we are on a time sequence for July 12th, 2012, when we had an extreme class solar flare. So that burst of light that you see there, that flash of light, that's called a solar flare. And we measured that in X-ray flux. So this is one of the high intensity flares because it's extreme class. And flares are basically bursts of radiation because of the release of magnetic energy associated with the sunspots that we just talked about. They're one of the solar system's largest explosive events. And what we're looking at here is a 3-hour loop of that data, that brightening. But let's also look at another channel on SDO. This is a hotter channel. This is actually 10 million Kelvin. And the flare is so bright here and so hot that it bleeds and saturates the CCD here along this line. And you can also see a diffraction pattern, cross-shaped, that's formed there because of the flare brightening. And flares emit in nearly every wavelength of the spectrum, and they can also accelerate particles. Their radiation can ionize the Earth's upper atmosphere, and that enhancement can cause blockages or even distortions to radio signals that we are transmitting on the Earth. But that really affects the high-frequency radio communications. That's 5 to 35 megahertz. So the effects that solar flares has on blocking radio communications on the Earth, that's what we call space weather. Next, let's go back to the coronal channel and let's talk about eruptions from the sun. So we're extending the time sequence a little bit, and it's hard to see, but just after the burst of light, look around in this area here. near the active region, near the flare, and you'll see that some field lines start to open up. And that's because we have a coronal mass ejection, and that's the eruption of mass and magnetic field from the sun's corona. So coronal mass ejection, and we call them CME for short. But we're going to zoom out a little bit here because we can see CMEs much better in a different instrument, which is called a coronagraph. And the ones we're going to be looking at first are from SOHO, that's the Solar and Heliospheric Observatory. That's located near the Earth, between the Earth at the L1 Lagrange point. So the Earth is over here. We're going to turn off that SDO label. And we have the SOHO label right there. That's the L1 Lagrange point. That's 1/100th the distance between the Earth and the Sun. And now you can see these lines showing you the SOHO viewpoint of those two coronagraph fields of view. A coronagraph is basically creating an artificial solar eclipse. So we're blocking out the sunlight from the central bright part of the sun, outer corona. And now we're playing a time sequence, and you can see those clouds leaving the sun. Those are called coronal mass ejections. So there are billions of tons of matter are erupted with every coronal mass ejection, and they're accelerated up to several million miles per hour. So they're moving very fast, and they can impact Earth in about 2 to 5 days if they're traveling in the right direction. They can really erupt in any direction at all. As you can see here, they're going all over the place. This black area you see here in the larger field of view is actually the handle for that instrument holding the circle in place to block out the central part of the sun to allow us to see the faint corona and the eruptions. You can also see the stars back here. All these dots that are going by, those are the stars. Now we've talked about flares and also CMEs. They sound kind of the same, but they're not exactly. They're similar because both of them involve the release of magnetic energy from twisted up magnetic field lines on the sun. Just the same way if you twist up a rubber band and then you let that go, it releases that energy. That happens for both flares and CMEs. But flares are just intense short bursts of radiation that last minutes to about an hour. But CMEs are actually eruptions of the mass and magnetized particles hurled away from the sun, and those take a few days to arrive at Earth orbit. Now, flares and CMEs can occur at the same time, but they can also occur independently. So now let's zoom in a little bit to the inner field of view of the SOHO coronagraph, and we're going to switch to the July 12th time period so that we can see what the CME looks like from that flare that we just talked about. So we're just doing a short loop here, and we're going to pause time, and you can see this cloud coming out. I can't show you any more data because there was a data gap after this time because, you know, spacecrafts don't operate all the time, the operations. But what we're going to do here is zoom out a little bit. And because it's sort of like encircling the field of view there, that tells us that the eruption is coming towards us. But now we're looking at the stereo A coronagraph field of view, because that also has that instrument. And now let's play that time sequence, and we can see the stream of material coming off of the sun. So eruptions, this eruption is about 3 million miles per hour, so that's faster than average. And you can see it's just streaming out into interplanetary space. So now let's rotate around, pause time, travel around to stereo B, and let's see what it looks like from stereo B's viewpoint. It really helps scientists to have multiple viewpoints of these eruptions so that we can get a really three-dimensional idea of what's going on. All right, so from this viewpoint, you can also see the stuff streaming out, and you can also see Earth is sitting there, so you can really see that this eruption is going straight towards the Earth. Now we can measure the speed, size, and direction of the eruption by having all of these viewpoints. And that can be used to drive simulations. And we're going to be showing you those simulations next. So let's first zoom over to the Earth viewpoint, look at SDO again, and we've turned on that coronal model. And we've also turned on the magnetogram observation from SDO. And that's because the solar wind model that we're going to show you uses the magnetogram observation, the observations of the photospheric magnetic fields, and the coronal field lines to drive the solar wind simulation. So we're also going to zoom out a little bit here. And that's because our second simulation, it starts at a distance of 21 solar radius from the sun. So you can see the boundary there. We're going to turn off those coronagraph images and just zoom out there. We're looking at the map of the sun in the ecliptic plane. And now let's turn on time. And we want to go back to, there we go. So this is a time period where we're just looking at smooth rotation of the sun spiral. And the magnetic field lines are colored by the solar wind speed. So Alex, could you put up the color bar for everybody? So we're going from red to yellow to white, where red is slowest and white is the fastest. And the magnetic field lines are also where the particles have to flow because they're charged. The sun, on average, is rotating about once every 27 days. So that's why we get this spiral, because it's sending out a stream of particles time. Similar to if you have a rotary sprinkler to water your garden, it's sending out water and rotating at the same time. Now, the sun's magnetic field actually extends all over the place, not just in the ecliptic plane, but just to make it more clear, we're showing it to you here, just in this plane. So now let's, so I want to also tell you the solar wind speed, if you measure it at Earth's orbit, is about 1 to 2 million miles per hour. That's really fast, right? But it's actually pretty weak because it only has 100 particles per cubic inch. So it's not like the winds we have on Earth. 100 particles per cubic inch is 10 times better than any vacuum that we can achieve on Earth. So it's pretty much empty, but solar wind is moving very, very fast. So next, let's look at the simulation when we have the coronal mass ejection, the CME going through. So we turn the coronagraphs back on so you can really see the eruption travel from the coronagraphs into our simulation. So you can see this wave coming out. So we use the speed, direction, and size measured from those coronagraphs, and we insert them into the simulation as high pressure gusts. And this is very similar to hurricane tracking. So we can see where they're going to go and what time they're going to arrive. It's a very important part of forecasting. And I was actually the one on Space Weather Watch when we predicted this eruption. So I remember having to figure out hit the Earth and what time would it hit. This one actually hits the Earth 2 days later. And let's also turn on, we have a of temperature to show you how big the CME actually is as it leaves the sun. All right, so what you're seeing there, we have a short time period where we're showing you the volume time step. There we go. So this big cloud that you see here is tracing the CME in temperature. So it's really large. It looks kind of small as it leaves the sun, but it expands out and it's really this very big structure. And there you can see it approaching the Earth. So the effect that CMEs can have is part of what we call space weather. And Dr. Masha Kuznetsova is going to talk to us next about the space weather effects on the magnetosphere.
Okay. So our heliosphere is huge. So having one model to track the space weather from the sun to the place where we live is not enough. We need a big range of models covering different spatial and temporal domain. So while Oscar is zooming closer to the place we live, we will use the space weather modeling framework developed by scientists at the University of Michigan to simulate the area around the Earth, which is the size comparable with the sounds of the sun. So Oscar, please turn on magnetic field. Yeah, so you see the Earth, and this Earth sits in the center of a magnetic bubble. These yellow lines is magnetic field lines that Leila talked about. This configuration called magnetosphere, it's formed as a result of interaction between Earth's intrinsic magnetic field and solar wind flowing outward from the sun. So what Earth's intrinsic magnetic field is pretty simple. It's actually like a dipole magnetic field that's produced by the bare magnet. So if you imagine, take a giant bare magnet, put it in the center of the Earth and tilt it with respect to Earth's rotation axis, an 11-degree, we will get Earth's magnetic field. So this feature of Earth's magnetic field used in compasses. So if you take a compass, it will show you towards the North magnetic pole. So it's not exactly to geographic North Pole, but pretty close. And compasses have been used by humans for centuries, at least for finding direction, at least since 11th century. And of course, people also use stars for navigation. And here in Planetarium, I don't think you should use compass, but the stars that you see in the dome, they're actually in correct locations, and we will start moving, Earth around. You can orient yourself.
You can see the big difference just behind the magneto tail there.
Yeah.
Yeah.
So
North.
now to see actually where the sun is, Oscar, please turn on solar wind. What also is now, and thank you, I forgot sun, is to give you an idea of direction of Earth's magnetic field. So it's going from south to the north. And it's very important. Again, we understand. So now we turn it off and we'll put solar wind. Yes. So that is model. So flow lines also come from the model. Everything is simulated using very sophisticated system. And it's flowing around the Earth. So you don't see it far. It's because, as I told you, the simulation area is not that huge. We start simulation from 32 Earth's radii towards the sun. And by the way, because we are just in different special sizes now, not in miles and not in solar radii, but actually in Earth's radii. And Earth's radii is 4,000 miles. So. And a spacecraft that measures the solar wind, it's located 200 Earth's radii towards the sun. So you can fit one sun here. So now we are looking from the North Pole, and you see that solar wind is deflected around. So because plasma cannot penetrate across the magnetic field, so it's moving on. So this magnetosphere, it's work as a shield. It's shielding us from the solar wind. It's also, we can call it like an umbrella. It's protecting us from elements coming from the sun. But the dangers of solar wind are actually different kind. We will not get wet, but if you didn't have a magnetosphere, the solar wind will wipe out the ozone layer, and the Earth would be subjected to very dangerous ultraviolet radiation. So this magnetosphere is saving us. It's really, our shield. And Oscar, please turn on geosynchronous orbit. So there is in the area somewhere between 6 and 7 Earth's radii, a lot of commercial and research satellites are orbiting. And this simulation is for very nominal quiet conditions, very typical during solar minimum. And as you can see, the satellites that orbiting geosynchronous satellites are all safely inside, and a lot of our technology depends on this satellite. But if the CME will hit, and we will talk about that later, the whole pressure of the solar wind flow can increase 50 or 100 times, and then the magnetosphere will change its shape. So actually, just to describe how it's look, and you already can see that magnetosphere not really symmetric as a bar magnet. The part that points towards the sun is compressed because of the solar wind, and the part that pointing away from the sun is called tail. So the most sunward part, you can call it nose, and or you can call it day side because it's lit by the sun, and the opposite side you can call it tail or night side. And this boundary between green and black, it's a bow shot because it's ultrasound, it's very fast solar wind. So it looks like a comet, but if we have very strong pulse or gust of the solar wind, this day side magnetopause, our shield, will be pushed back to the Earth, and then slightly outside the shield and will be exposed to this hazard condition. So, spacecraft operator really need to be to know if it's happened and when, and how to take care of that. So you understand now that really the shape and size of magnetosphere depends on the density and velocity, sort of pressure of the flow, but it also depends on the magnetic field that come to us from the sun, and what's most importantly, on the direction of magnetic field, if it's parallel or anti-parallel the magnetic field of the Earth. So let's just show you how big of a difference it will be. It will take different directions. So please turn on northward in the planetary field. Yes, that is the situation when magnetic field that come from the sun and is showing in green. It's in the same direction as Earth's magnetic field. So the motion, the particles show you the direction of the field, and it also shows the magnetic topology, so how these magnetic lines are connected. Green lines have their both ends in the interplanetary space, while yellow, that's magnetosphere lines, they have their both sides pointing to the Earth. So our magnetosphere is yellow. Everything inside this yellow region is really well protected. It's the magnetosphere for this northward case is very close and pretty boring. So solar wind for a long period of time look like this. Magnetosphere is not changing much. It's not much, fluctuation of magnetic field. Now, the only thing what we will do, we will flip the direction of magnetic field in the solar wind. Yeah, Oscar, please do that. Yes. So you see the configuration completely different, and you can see, sorry, pointing wrong direction. So here at the nose, there is two magnetic field with different polarity mid. So this magnetic field that's showing north, this is southward, and somewhere in between the magnetic field is almost zero. So when the magnetic reach just disconnect and then reconnect with other one, and this process called magnetic reconnection, it's really releasing energy of the magnetic field in the energy of particle motion, and then we form a new brittle film line. And also, can you make them brighter, please? Yes. So this red film line that's new, we didn't see them before. So they form just out of these two lines. So out of one yellow, one green, we have pair of red. But what's important, these thin lines have only one end in the Earth. So all elements from the solar wind can directly enter. And this boundary between red, talk about that more, than yellow, it's actually accelerated particle from reconnection just go directly here. But it's, that situation already become very disturbed space weather. These red field lines also carried towards the tail side by the solar wind, and they reconnected again in the distant field lines. So during these processes, we have more and more on this red fin line. So we are pumping energy, magnetic energy, into the magnetosphere, and magnetosphere can take only so much. And so let's see how actually it will do that. So Oscar, can you show that time sequence? So it's will now show a time sequence for the same configuration, the same solar wind condition, nothing changed, but it's pointing southward. Magnetic field lines are painted in temperature. So you'll see now that all reconnection heating plasma. So the tail is stretching, the loading energy. So now it will have too much. It wants to get rid of that. So actually what Magnetosphere is doing is ejecting the big portion of its tail. So that's called plasmoid. What plasmoid is a like a cylinder or a blob of plasma, and magnetic field line draped around that. So it's it's very dynamic process. Magnetosphere hedge that plasmoids probably every hour. This big one, it's also sometimes it's doing it much more frequently, and smaller one every 12 minutes. So scientists still want to understand how it's happened. So I guess we have enough just to illustrate you that model case. So we will now do the real stuff. And I mean, we will take a real solar wind data observed at the ACE in July 2012. So Leila showed you the CME initiation at the sun in March 12, 2012. It's reached the ACE spacecraft around and by still day, probably around p.m., but it's not, New York time. It's actually the time, universal time, so it means times in Greenwich. So I think we start simulations. The yellow is last closed in lines. You see just synchronous orbit. So we start simulation several hours before the CME hit. The blue line is flow line. They show the velocity. So we will wait a little bit. I don't know what. Oh, yes. So it's hit us. It's a little bit, and it's more and more and more. So that's what happened with magnetosphere when this, shock arrived. And now, Finland is not blue anymore, they're green. So it's actually the solar wind is faster, and it remained this fast for probably 3 days. Now we will replay this again, but we will color flow lines in density. The density pulse lasted probably for 12 hours, a little bit later, maybe 30 minutes after the velocity pulse. And we will look at from the side now. So then you can see when the density pulse arrives, we will start squeezing magnetosphere like a toothpaste. Yeah. So it will come slowly. So you see how dynamic the magnetic, how far it's stretching, well beyond the lunar orbit. So yes, the shocks start arriving, and there will be more. Yes. So that's CME. When it's hit the Earth, it significantly disturbs the magnetic field. But the magnetic field, they are mapping towards the Earth, and in a boundary of magnetosphere, it's only on 3 Earth's radii, but there is other models who will map it. Yeah, there is another, more and more. So these magnetic field lines, they actually go all the way to the Earth, and the huge network of magnetometer stations, they can measure this perturbation. So that's why it's called geomagnetic storm, because on the insulation of magnetic field. If you're in higher latitude, your compass will not work well, but there are other dangers related to this fast variation of magnetic field. So if you change magnetic field very fast, it will induce currents. And if you have conductors on the Earth, the current will flow through these conductors. And which conductors we have? It's our power lines. So this is called geomagnetically induced current. And if, storm is large enough, these currents can be huge and they can actually burn transformers. And there were, times, I think the biggest, sort of power failure was in 1989 when the storm in March of this year knocked out the entire Quebec power grid station. So for almost 12 hours, there were no electric power in Quebec whatsoever. And, there's other storms, was in probably big storm in 2003 in November, so it's called Halloween storm. And in Northern Europe, there was a lot of power failure in Scotland and in Sweden. And again, some power companies in the US demonstrated, reported some problems. So there is really serious issues. The biggest storm, this geomagnetic storm on record, it was actually in 1859. It's called Carrington event. At that time, we didn't have power grids and sophisticated technology, but there was telegraph. So, and the storm was so huge that entire telegraph network in Northern America was failed. And there was, burns on the power lines and fires were reported. So if storm like this will happen now, we will be in big trouble, because it's not just local phenomenon. It's not only Quebec. If it goes to low altitude, it can, affect many countries. So now, U.S. government and the whole world is really seriously looking on space weather. But basically because of our technology and dependence on technology. So now I think you enjoyed that view. So let's just try to replay it again, but we will make a color-coded in temperature. And the temperature is just because the storm is, as I told you, because of magnetic reconnection, it's hitting. It's hitting the plasma. So magnetic energy transferred into thermal energy, in the flow, in the velocity, in the kinetic energy. So everything started nice and cool, so blue, and colors go from blue to pink to red to yellow to white. And then when storm proceed, we'll see things are getting brighter, especially, around this geosynchronous orbit. So the satellites on the geosynchronous orbit environment around them is changing. So unfortunately, we don't have volumetric visualization, but even along these thin lines, you see a lot of red spots around, the geosynchronous orbit, even white. So it means the satellites suddenly feel much more, particles flowing into its surface, and it can cause different types of effects. One of them in this energy range is surface charging. And during the storm that actually was weaker than this one, in 2010, the European communications satellite, it was in April 2010, just during the storm like this, when it was located the most, bright area, it lost control completely. And it's turned into zombie satellite, and it was in this state for almost a year, but then they managed to bring it back. So really our dependence on all this technology in space, we need to look at space weather more closely. And now let's turn the last one. I think that this thing is really beautiful. It looks like sea creature. So you can enjoy how it looks, but it is real thing. We live here. It's, that's what around us. So sun look fantastic. So it's simulations, just not pretty picture. This is simulations of real event. And Leila was on duty when the simulations have been done. So, okay, enough of this sea creature. Bye-bye. Let's go to this other look. So we're now simulating only the last part of the storm. Why this storm is somewhat very interesting, because the last probably day and a half, the interplanetary solar magnetic field was southward. So it was staying along southward. So that's when this reconnection play a role, and we have a big area of this red field. And the particles that accelerated by reconnection, they flow along thin lines toward the Earth. So this, green and purple, it show you the fluxes of electrons toward the Earth. So again, as I told you, this model is only on 3 axis radii, but we can, map that to the, closer to Earth ionosphere and atmosphere, and it's look like aurora or polar lights that probably some of you see. So it's beautiful. Goddard call it magnetosphere eyelashes, which I like it. It's really cool. But you cannot see. We are not modeling, the formation of aurora. Aurora, or not northern light, it's actually forming the results of these particles. They go along thin lines. They get in the area between, and then electrons. Hit or excite molecules, and then they emit light. So what you see, it's a model, it's called the Bayesian prime model. It developed at Johns Hopkins University, and it's model the location of aurora. It's semi-empirical model based on a lot of observation from polar crossing satellites. So you see only still image, but it's actually dynamic model. It's very heavily used. So you see the change of aurora. We're showing it only during that period, the most bright one. And it's pretty accurately predicted the location of aurora. And some people who observed the aurora actually, did model data comparison, some citizen science, and it was very good shape. Comparison. What's another thing I want to tell you, that this fluxes that's flowing into the ionosphere, they are also affecting our communications, changing the electron content of the ionosphere. So that really affect communication, GPS. So we need to be able to model it better. Then another important impact of space weather, that it affects the content of density in the neutral atmosphere, and that the neutral atmosphere can slow down satellites, result in satellite drag, which actually can cause collisions. So it's a lot of attention need to be put to that. But these images are beautiful, but it's much more beautiful if you really see the aurora. And if the storm is big, you can see it and at low altitude like New York. But if you want to see it during regular time, you can go to northern. Put the International Space Station orbit. Yeah, good. Can you turn International Space Station orbit? And so that pictures that Carter showed, it's actually taken from International Space Station?
Yes, and this is of the Aurora Australis, which we had been looking at. And this is from the ISS during this period and this storm that we've been talking about. And what we see up north, it's hard to see which continents. That's North America going by right now. And Oscar, could you fly back up northward? There you see the lights of North America going by. Great. And so this is the north side, but this is July, and then so we have this illumination. It's daytime up there, and thank you, Leila. So this is the Aurora Borealis. The Australis is on the other side. Once again, North America going by. We saw the city lights, and from up in this perspective, looking, we see down some bright stars along one side of the Earth here. And that's Alpha Centauri, the nearest star to us. And so can we go down to the South Pole, please? And these lights of India, lights of the Middle East. That's the Nile River valley there. And so here we see the Aurora Australis. And at this time, it's the south polar night, given that it's of the midnight sun at high latitudes of the North Hemisphere. So here we can see this visualization better. And at the time rate that we're going, the Earth is spinning quite fast, but the International Space Station going around the Earth every 90 minutes. And it's only about 250 kilometers, or about 400 miles up. So I think we're going to turn this back to Leila, who's going to finish off the program. And here's the laser. And thank you, Masha.
So Masha talked to us about the effects on the magnetosphere from the CME, geomagnetic storms, and effects on the ionosphere and satellites. But there's one more effect. So we're going to zoom out and take a look at the solar wind simulation. And so we're going to turn Enlil back on, and Oscar is in the driver's seat now. He's piloting us. So we're turning Enlil back on, and we're turning on our CME simulation. And Enlil was actually developed by Dr. Dušan Ostrasil. And so we're looking at the same color map as before, but now we're going to change that to a uniform color, so we can turn that off yet. Thank you. And then we're going to show you the magnetic field lines that are connected directly from the sun to the Earth, which is located there. So thank you, Oscar. And now let's turn on the particle flows along those magnetic field lines. And these particles that are going to be coming from the sun, you'll see them in a moment, they're called solar energetic particles. And they travel along these directly connected magnetic field lines. And you can see the wave of the CME here. They can also be accelerated by that wave as they pass through. And their speed is nearly the speed of light. That's why they're called energetic particles. And these can harmful radiation at the Earth, where they connect to the Earth for the astronauts that are in orbit at the space station, and also for polar aviation. So flights that end up kind of inside of the auroral oval that we just showed you, they're at an increased risk for radiation. So that's another space weather effect, is from the solar energetic particles. But now let's turn off the simulation, and we're going to have Michael pilot again, and we're going to go back to the sun. And we're going back to the sun because the active region that produced the activity on July 12th wasn't finished producing activity. So let's go back and take a look at it. So we're going to turn off Enlil and fly back to the sun. And we're going to turn on one of the coronal channels from SDO. And we're going to take a look at this large active region as it rotates off the disk as viewed from Earth. So that's our active region right there. And if we play time, we'll see that it's rotating off our Earth viewpoint from the stereo A viewpoint. So let's fly around, let's pause time, and we can catch the rest of days later on July 17th. So let's rotate around a bit. And then, so there we can see these regions showing up as we fly back around. And we're looking at the plane as well, so you can see the sun's outer corona very nicely. And time is now July 17th. You can see the region rotating back around. Now on July 17th, 18th, and 19th, we had 3 eruptions, so a sequence in a row. 2 of them came from this region, and you'll see there's one that came from there as we run through this sequence. So there's a lot of activity happening there. These were all sending eruptions towards stereo A roughly. So let's zoom out a little bit and take a look at the coronagraph image from stereo A to see these CMEs. So we're going to turn on the coronagraph, and we're going to start time for the sequence. On the 17th, there's 1, and then we have another eruption, and then there'll be 1 more at the end. There we go. So all 3 of these are headed towards stereo A, traveling at 2 to 3.5 million miles per hour. But the really spectacular eruption happened a few days later on July 23rd. So let's go to July 23rd. And now you'll see this eruption of material, kind of like a halo that we saw earlier. So it's coming straight towards stereo A. And then we can see this noise in the detector, this sort of streaks. And that's because it also produced one of the largest solar energetic particles ever observed. And the CME here was actually moving at 5.5 million miles per hour. That's one of the fastest CMEs ever observed. So let's zoom out a little bit and take a look at the Enlil simulation, the solar wind simulation for this time period. All right, so let's change this to loop over from the 17th all the way until the 23rd and onwards. So there's our first CME, second, and then third, and then now you'll see the big one coming out. There it is. So it really saturates the color scale. It's huge. It's traveling through there, and it really rams right into stereo A. Now this arrived at stereo A just 18 hours after it erupted from the sun. It's really fast. And scientists for a while were trying to figure out why it arrived so quickly, and its speed decreased not that much by the time it got to stereo A. It was still traveling at 4.5 million miles per hour when it hit stereo A. And now we think that maybe the 3 CMEs that came before it, the ones that you're going to see coming out now, came out here, 1, 2A. So they cleared out the solar wind, very little particles there, so that the final one on the 23rd could kind of travel through unimpeded. Now, if this had hit the Earth, this would have produced the second largest geostorm ever observed. And Masha mentioned that that's the Carrington event. So we're lucky that this one wasn't traveling towards the Earth. So now let's zoom in a little bit to the stereo A coronagraph. And we can turn off the Enlil simulation. And I just wanted to wrap up here and tell you that we've been talking about a very interesting period in space weather. And space weather refers to the effects and the conditions on the sun, in the solar wind, throughout the solar system, and near Earth that can affect our space technology or ground-based technology, and also endanger human health. And the sun is ultimately the driver. The sun and its magnetic field ultimately drives all space weather activity for us in the solar system. And let's turn on the last slide with the solar eclipse. Yeah, so I wanted to let you guys know that you can look at a natural solar eclipse on August 21st, 2017. It's going to travel across the US, and similar to the artificial eclipse that we have in the center of the dome, the natural eclipse, we're also going to block out the sun's light, and you could see the sun's corona with your own naked eye for just over 2 minutes. It's going to travel across 14 states from Oregon to South Carolina. That's the path of totality, where the moon completely blocks out the light from the sun. And we can really start to see into the inner corona. And that's something we can't do with the artificial eclipse images that we make with the coronagraph. So no technology, no instrument can get down to that level of detail. So it's a really exciting opportunity for scientists to learn more about the corona, but it's also really exciting for you all because you can see the corona yourself
and
with
Leila,
your naked eye.
I'd like to just mention that this eclipse, which of course is cutting across so much of the United States, has been an excellent opportunity to consider and plan ahead. The NASA funding that we received to do OpenSpace, about $6 million over a 5-year period, which is enabled by our enabling a collaboration not only with Sweden, which has been going on since 2002, but with New York University's Tandon School of Engineering and University of Utah's Scientific Computing and Imaging Institute. We were one of several awardees, and one of the other awardees is actually setting up cameras and standardized telescopes and cameras across the path, across the US. And the goal will be to create a longer movie, because we may only have 2 minutes of totality per site, but this will enable a movie to be put together. And we're looking at possibly collaborating with them for further visualization, so stay tuned with this. And I also just wanted to thank you all again for coming, because really OpenSpace began with the CCMC team, we were too busy on a production called Dark Universe. And so really the first work began with Masha and her team and Leila. And also I want to thank Asher Pembroke, who's in the audience, and with his family. Maybe, did he take off with your son? One of the children, they couldn't take it anymore. But I also want to give a shout out to another student from Linköping. Actually, there were two. One just went home. But Richard Lindstedt, Richard, can you please stand up? He came in and did tireless activity all weekend with this team to make this happen. And today is his last day. And some of you who came to the Mars program may have seen a little bit of the surface of Mars that Richard and Michael have been doing. This is visualizing the terrain from the rover itself. And he just ran all the models, so we can now actually go over 5 years of history of where Curiosity landed on Mars, right on up to about a year ago, because they have sort of well, it was about a year ago. 3 months ago. Okay, great. We had an update, which is great. So I really want to thank Masha. I want to thank Leila. We'll open it up for questions, but thank you so much for coming and sharing this. And I want to thank, last but not least, please stand up, the team here in the pit, Oster, Michael, and Alex. Great.
Thank you, everyone. That was just absolutely amazing. The best graphics I've ever seen. Wouldn't you agree? Real-time data, real-time analysis. Just absolutely fantastic. We have time for a few questions here in the dome. We'd love to get to some of our young scientists, so don't be bashful. If you have a question to ask our scientists, by all means, let me see a hand raised. You have a question? Yes, okay, we have a question right here.
Are solar eclipses more effective on sunspots or no?
Well, I guess maybe how do solar eclipses affect sunspots? Are there, is there more of more sunspot activity when we have a solar eclipse? Good question. Thank you.
Yeah, so sunspots are actually completely unrelated to solar eclipses. Eclipses have to do with when the moon's orbit aligns perfectly to block out sunlight from the Earth view. But the sunspots, that's caused by the sun's magnetic field, and that goes through an 11-year cycle. And right now we're in solar minimum. Great question.
We have a question right back over here.
Yes, hi. Great presentation. My question was about the magnetic orientation on the Earth's pole. It seems like in the last several decades, it's been accelerating it's been accelerating towards the magnetic pole's been accelerating towards the actual. And I was wondering the relation between the Earth and the Sun as far as that goes, as far as the declination you have between two planets, between the Earth and the Sun. And if you can elaborate on that, thank you.
Yeah, so of course, when I say Earth is dipole, like a magnet, bar magnet, is not exactly true. It's the most, the strongest components of the Earth's magnetic field is the dipole, but it's changing all the time. Magnetic pole is changing all the time, but it depends not because of the sun. It's internal Earth process. So because the Earth's rotation, there is a core of the Earth, so the geomagnetism that's formed. So there is a group of scientists that actually every 5 years, they are reevaluating and writing a new model of the Earth's magnetic field. There is South Atlantic anomaly where actually magnetic field is very strongly deviated from the dipole field, but it's not because of the sun. So sun is not affecting that. But each time when we want to model more carefully, we need magnetic field to really make a prediction.
We have a question up here.
careful as
A few years ago, I believe, one of the stereo, I can't remember if it was stereo A or stereo, and they weren't sure if they were going to be able to get plans to attempt with like the last of its fuel or something to get it back online in 2017. I didn't know if you had any updates on that, and if in your perspective, what this kind of gap in data from one of the satellites is going to cause for, heliophysicists understanding of our sun.
Yeah, that's another great question. Yeah, it's true. I didn't mention it to you, but I had completely forgotten. But stereo behind spacecraft, we've lost contact with it. And I think that happened in December 2014. And the star tracker broke and it couldn't keep track of where it was going. And now it's freely spinning. And so we can't contact it. And it happened right when it was directly behind the sun compared to the Earth's viewpoint. So it was very hard to send transmissions straight to it. So we really had to wait for it to come around. And we've used a lot of satellites, radio telescopes on the Earth to try to contact it. So there really was a really big push to try to do that. And we regained a little bit of contact, but it wasn't fully successful. So we're waiting for it to continue to trail around. It's passing back around, and we're going to keep trying. So right now we don't have contact, but it does make a huge difference. So now we only have 2 viewpoints to understand the coronal mass ejections. And actually, I have an undergraduate student who just did a study to see what impact that has on how well we can predict the trajectory of these CMEs as they propagate through interplanetary medium. And we think that it gives us an error of about 2 hours. So it adds on to the error.
We have a question right behind you.
So how able are we to predict these solar flares? Are we able to know when they're going to come, or do we have no idea?
Yeah, that's another great question. Yeah, so we were really bad at predicting solar flares because they happen so suddenly and because there's the release of magnetic energy associated with them. Same with CMEs. We don't know if they're going to happen from the regions. So we have some ideas, like we see precursors of some signatures in the SDO images that you saw in the extreme ultraviolet, and we might have some idea when we see increasing. That tells us there's a high probability. So for now, we put out probabilistic forecasts for whether or not there will be a flare, but it's very much an area of research.
We have a couple, I'm sorry, go ahead.
Yeah, at CCMC, we actually, if you're interested, we can provide you more information, but in our center, we have public website, and we're running a lot of flare models, flare predicting models in real time. We actually have international flare predicting challenge. So people trying, to predict the flare, and then when the flare appear or not, we are giving them some scores. So it's very exciting to to trace it. We do the same with CME prediction and so on, energetic particle prediction. So if you are interested, you can go on our website and follow this.
We have a couple of more questions from our young scientists, and then we're hoping you can all stay a little longer while we leave and answer more questions if we have them. Here we go.
If an astronaut goes beyond the magnetic field, what would happen to him?
Very good question. What would happen to an astronaut if he goes beyond that field, or if one of those CMAs comes near him?
Yeah, so what would happen then is that it's not inside of the magnetic bubble of the Earth anymore. It won't have a shield. And that's another really great question. So people are talking about manned missions to Mars. So there's teams of scientists working on how to mitigate the effects on the astronaut. So when I showed you the flows of the solar energetic particles, the really high speed particles coming from the sun along the magnetic field lines, the astronauts would all of a sudden be really exposed to a high dosage of those particles. And so they would have increased radiation, and they can get radiation poisoning. So what they're trying to do is figure out how to shield their spacecraft if you were to send a manned mission to Mars.
And we have one more question.
I was just wondering how the solar wind affects other planets based on their different magnetic fields.
That's a great question.
Actually, other planets have also magnetic fields. Some of them do have, some of them don't. For example, Mars has a magnetic field, but it's not dipole at all. And, we also do more simulations of that in solar wind interaction with Mars, solar wind interaction with Jupiter and Saturn. I think Carter have some sort of build a tone here where a lot of models come and visualize that. So yes, it's very similar situation for some planets. For some, like Mars, it's very different. Venus doesn't have magnetic field at all. Mercury have very weak magnetic field, magnetopause, this boundary. It's actually only a fraction of Mercury radius. And, everything in Mercury going so fast. What's here I showed you, and the time scale is hours. 10 minutes is fast. In Mercury, everything goes several seconds. It's like a smaller version of the Earth. So it's, we're doing simulation of that too. We can do this program.
We're working toward a visualization of the Europa Clipper, which will map Europa. Just one second. So the Europa Clipper will be orbiting in and out of Jupiter's magnetic field. It's the largest magnetic field other than the sun, and it's the largest planetary magnetic field. And so the spacecraft has to sort of, it doesn't orbit Europa, which is in the radiation belts. So it orbits in and out. So it's like 45 encounters. It's very complicated, but we're good friends with principal investigators designing that mission. So we're going to show that. So I know there's one more question.
One more question.
Thank you. Very interesting. Is there another element of the solar weather, space weather phenomenon that you would like to be able to measure? And is there on your wish list? Is there another satellite telescope that you'd like to have that would help you do that?
Yeah, there is a lot of we have on the wish list. We really don't have enough, and it's really for us, for like modeler, for scientists. If you want to model, we need to put good observations as input to the models. But if we put bad observation, garbage in, garbage out, and even this solar wind monitor having problems, not really problems, it's just getting old. Many of this data that we show, it's research satellite. SDO, stereo, it's all research satellite. Their life, was supposed to be a few years. They are not, were designed to be this operational. Now, NOAA, NOAA sweeps in Boulder. They are official forecaster for the, the public, for the commercial and government of space weather. So they need that for their prediction in operational. And there is really not much we have. So yeah, it's money.
I was hoping that we might have a couple questions because we were streaming live on YouTube. So if you want to revisit this and look at this, you can go to YouTube. I would go to get the address, go to OpenSpaceProject.com, and you can relive the program in YouTube 360. So not demonstrating on my phone, but with the accelerometers, you can look around. And so that's unique. First time that we're doing that. We're hoping to do that more with the OpenSpace public programs that we're doing. I want to thank you all for coming, but I really want to, once again, please put it together for our friends from the CCMC team. Masha and Leila, you did a great job. Thank you so much. And our master's students, this is their project, and this is the first time they're flying the dome, and this is the most amazing graphics I've seen in the dome. Oscar and Michael, thank you so much. Thank you so much for coming.